Hello, welcome to Introduction to Composites MOOC course. Today is the second day of this week, which is the 10th week of this course. Yesterday, we had introduced relationships between engineering constants and members of the compliance matrix, which is the S matrix, the engineering constants and the stiffness matrix elements, and also the interrelationships or relationships between Q and S matrices. So, we will have a brief recap through an example and then we will move on to the next topic. So, we will do an example. So, the example says that we know all the engineering constants of the material. So, EL is 148, ET is 10.5, GLT is 5.61 and nu LT is 0.3, and all these are MPa. Of course, Poisson's ratio is not in megapascals, it is a dimensionless number. So, with this information we have to find the Q and the S matrices. So, we have to find the stiffness matrix and the compliance matrix. So, that is what we want to do. So, the first thing is we know nu LT and this nu TL gets used a lot of times in these relations. So, nu TL equals nu LT times ET over EL. This is a relation we already know. So, this works out to 0.021. Now, Q11 equals EL divided by 1 minus nu LT nu TL, and that comes out to be 148.95. Q22 equals ET divided by same thing, and this is equal to 10.57. Q12 equals nu LT ET divided by 1 minus nu LT nu TL, and if you plug in all the numbers you get 3.17. And finally, Q66 is equal to GLT, and GLT is already known. So, that is 5.61, and the units of Qs are MPa. Okay. Units of Qs are MPas. So, all engineering constants do not have the same unit because nu LT is dimensionless, but all Qs they have the same dimension and the unit, which is MPa. Then next we do is S. So, S11 is equal to 1 over EL, and that works out to be 0.0068, and this is MPa inverse of MPa. S12 is equal to minus nu TL divided by ET. So, remember there is a negative sign here. I do not know if in the last class I had shown that or not. Yeah, there is a negative sign I had mentioned here also. So, just wanted to reconfirm. So, it is negative of nu TL divided by ET, and that works out to be minus 0.0020, and once again units are MPa inverse. And then S22 is 1 over ET, and that is 0.0952 MPa inverse, and S66 is equal to 1 over GLT, and that works out to be 0.1783 MPa inverse. So, once again Qs and Ss, Qs have a unit of MPa, Ss have a unit of MPa inverse, EL, ET, GLT have a unit of MPa, and nu LT is dimensionless. So, this is the conclusion on discussion for the how S, Q and engineering constants are related to each other. Finally, we will spend a few minutes on what kind of values the engineering constants cannot have. So, there are some restrictions. So, if you in your calculations or in your experimental results come across certain values of EL which violate the conditions I am going to talk about now, then you should be sure that either your experimental or result is wrong or your theoretical calculations are incorrect. So, the first set of restrictions are that all the engineering constants, they have to be more than 0 elastic constants EL, ET, GLT, GLT prime, GTT prime. So, all these guys individually they have to be more than 0, they cannot be negatives at all, just not possible, mathematically and physically not possible. The second set of relations are that these terms 1 minus mu TL times mu LT, 1 minus nu LT prime times nu T prime L and 1 minus mu TT prime nu T prime T. So, these guys also should be individually 0, more than 0, they cannot be less than 0, it will violate some basic laws of geometry and physics. So, this cannot be negative. And the final constraint is that 1 minus, this is a little long equation, nu LT, nu TL minus nu LT prime, nu L, excuse me, T prime L minus nu T T prime, nu T prime T minus 2 nu LT, nu LT prime, nu TT prime. So, this long expression should be more than 0. So, I have not gone into the mathematics of all these details, but it is important that when you are doing some experiments or calculations related to composite materials, make sure that none of these conditions are violated if your system is a unidirectional lamina and it is in the state of a plane stress. So, this is very important to understand. So, now we move to the next topic for this course, and this is about transformation of Q and S matrices. Transformation of Q and S matrices. So, I will explain what does all this mean. So, here is the current situation. So, in whatever we have learned till so far is that if I have a lamina and let us say this lamina is unidirectional and this is my L direction, this is my T direction, and let us say I have a sigma L on it, I also have a transverse stress sigma T and I also have some shear stress So, this is tau LT. Then if I know the stresses and the engineering constants or the Q matrix of this material, I can calculate the strains in the system and vice versa, and the relationship is sigma L, sigma T, tau LT equals this Q matrix So, here I have used the terms L. So, L corresponds to one axis, T corresponds to two axis, right. That is. But here in the current situation, the direction of loading and the direction of the material axis, which in this case is L and T axis, they are aligned. Okay. And if they are aligned, then we can use these relations. If they are aligned, then we can use these relations. But what happens if they are not aligned? What if LT directions are not aligned? And they are not aligned to loading direction. What if they are not aligned to the loading direction? That is the question. Then can we have, the question is, then can we have a similar stress strain relationship, and what will be the nature of Qs? In this case we have Q11, Q12 0, Q12, Q22 0 and 00 Q6s. So, what kind of stress strain relationship will be there and what will be the nature of Qs? This is the question. So, I will just want to make this clearer. So, in this case the picture would be something like this. So, this is my x axis, and in the x axis I am applying sigma x. This is my y axis, so I am applying sigma y, sigma x, sigma y, and I can also have shear stresses So, I have all these things, but the direction of fiber is different. So, this is the direction of fiber. So, here let us say this is my L axis and this is my T axis. Okay. So, in this case the L and T direction is not aligned to sigma x direction and the direction of the y direction. Now, this equation is good only, the first set of equations which we saw, it is good only when the alignment is there, then only we can write this equation. But in this situation we cannot use this equation right away. Okay. We may have to do some mathematical manipulations so that we can still use this, but this is what we want. So, what we want is, we want to develop a relation. And what kind of relation is that? We want to develop a relation such that, of this nature. So, here sigma is not measured with respect to LT axis, but with respect to x and y axis, and that is equal to some other matrix, and we will not call it Q, but we will call it some Q bar matrix, which is different than Q. We do not know what that nature is, times a strain vector, which is again measured with respect to xy coordinate system, because it is the xy coordinate system we are interested in. We do not care what is the LT coordinate system. The only thing we have, an additional thing is, that the orientation of LT with respect to xy coordinate is theta degrees. So, as theta keeps on changing, we have to figure out how can we relate epsilon, the strains, to the stresses in terms of this q bar matrix. This is what we are interested in finding. So, this is exactly what we will start doing tomorrow, and till then you please review all the material which we have covered till so far, because it will be useful. Also do a few questions from the book. You already have the details of the book, and we will meet once again tomorrow and continue this discussion starting tomorrow. Thank you.